Welcome to G Fun Facts Online. Today, we are looking upward, past the clouds, to an invisible battlefield that exists at 35,000 feet. Imagine you are sitting in a window seat, cruising at high altitude. The coffee is warm, the ride is smooth, and the autopilot is gently guiding the aircraft toward your destination. Outside, the sky is a serene, deep blue. But unseen to your naked eye, a violent storm is raging. It is not made of wind, rain, or lightning. It is made of high-energy particles, accelerated to near light speed by a massive explosion on the surface of the Sun, 93 million miles away. For decades, aviation safety focused on tangible threats like bird strikes, engine failures, icing, and thunderstorms. But as modern aircraft have transformed into flying data centers, a new, silent adversary has emerged. It is a threat that passes through the aluminum skin of the fuselage as if it were not even there, striking the microscopic transistors of flight control computers with the precision of a sniper. This is the world of space weather, and for the avionics engineers responsible for keeping planes in the sky, it is an escalating war between solar physics and software reliability. In this episode, we are going to delve deep into the invisible war between solar storms and aircraft software. We will explore the physics of the threat, the terrifying mechanisms by which a single subatomic particle can crash a system, and the ingenious digital shields, from triple redundant voting logic to self-healing memory, that engineers are deploying to protect the future of flight. To understand why a line of code in a flight computer needs to be hardened, we must first understand the enemy. Space weather is not a rare anomaly. It is the dynamic, often violent, environment of our solar system. The Sun is a magnetic variable star that periodically unleashes energy in three primary forms that impact aviation. First, we have solar flares. These are sudden flashes of brightness observed near the Sun's surface, essentially explosions of electromagnetic radiation, specifically X-rays and extreme ultraviolet light. Traveling at the speed of light, they reach Earth in just 8 minutes. Their primary impact on aviation is high-frequency radio blackouts. When these X-rays hit Earth's upper atmosphere, known as the ionosphere, they increase its density, absorbing radio waves rather than reflecting them. For a pilot over the Atlantic trying to contact air traffic control via HF radio, the line simply goes dead. Then, there are coronal mass ejections, or CMEs. If a flare is the muzzle flash, the CME is the cannonball. A CME is a massive cloud of magnetized plasma, billions of tons of solar material, hurled into space. It travels slower than light, taking 1 to 3 days to reach Earth. When it arrives, it slams into Earth's magnetic field, causing a geomagnetic storm. This can induce dangerous electrical currents in power grids and disrupt the magnetic compasses and GPS systems aircraft rely on. But the most critical threat to avionics hardware comes from solar energetic particles, or SEPs. Accelerated by the shock waves of flares and CMEs, protons and heavy ions stream toward Earth at relativistic speeds. These particles are the bullets in this battlefield. They possess enough kinetic energy to penetrate the fuselage of an aircraft, the plastic casing of a microchip, and the silicon die itself. On the ground, we are protected from this bombardment by Earth's magnetosphere, a magnetic bubble that deflects most solar particles, and the thick blanket of the atmosphere, which absorbs the rest. However, commercial airliners do not fly on the ground. They operate in the upper troposphere and lower stratosphere, where the atmosphere is thin. Furthermore, Earth's magnetic shield is not uniform. There is a weakness at the poles. Magnetic field lines funnel downward at the north and south poles, creating a particle funnel where solar radiation can penetrate much deeper into the atmosphere. This is why polar routes, which are critical for connecting North America to Asia, are the most dangerous sectors for space weather. Then there is the South Atlantic anomaly, often called the Bermuda Triangle of space. This is a region over South America and the southern Atlantic Ocean, where the inner Van Allen radiation belt dips dangerously close to Earth's surface. Satellites passing through here frequently shut down to avoid damage, and aircraft flying through it experience significantly higher radiation fluxes. As aircraft fly higher to save fuel and take more polar routes to save time, they are venturing further into the line of fire. Now, let us look at the interaction between a high-energy particle and a microchip. This is a probabilistic game of Russian roulette, known as a single event effect. Modern avionics rely on microprocessors containing billions of transistors. These transistors act as switches, representing binary data, ones and zeros, by holding a tiny electrical charge. When a high-energy neutron, generated when solar protons smash into the atmosphere, strikes the silicon of a chip, it leaves behind a wake of ionization, a trail of electrical charge. If this charge is deposited directly into the sensitive volume of a transistor, it can overload the circuit's voltage state. A transistor representing a 0 or low voltage might suddenly read as a 1 or high voltage. This is a single event upset, colloquially known as a bit flip. In a photo file on your phone, a bit flip might just change the color of a single pixel, which is unnoticeable. But in a flight control computer, the stakes are different. If that specific bit represents the sign plus or minus of the aircraft's pitch angle, a plane flying level might suddenly think it is pitching up 15 degrees. The software, reacting to this false reality, commands the elevators to pitch the nose down violently to correct an error that never existed. There are different types of these effects. A single event upset is a soft error. The hardware is physically fine, but the data is corrupted. A reboot or rewriting the memory fixes it. Then, there is the multiple bit upset. As chips get smaller, transistors are packed closer together. A single particle can now pass through multiple adjacent transistors, flipping several bits at once. This is much harder for traditional error-checking software to detect. The most severe is the single event latch-up, a hard error. The particle strike triggers a parasitic short circuit, causing the device to draw a massive current. This can burn out the chip physically unless power is cut immediately. In an aircraft, this looks like a permanent hardware failure requiring a system reset or swap to a backup. Paradoxically, newer, more advanced computers are more resistant to these errors. Actually, the opposite is true. To make computers faster and lighter, manufacturers shrink transistors. This is known as Moore's Law. Smaller transistors require less electrical charge to switch states. This means a lower energy particle, one that would have bounced off a chip from the 1990s, can easily flip a bit in a modern chip. Furthermore, a modern flight management system has gigabytes of memory. That is, billions of potential targets for a particle strike. The probability of some bit flipping somewhere on the plane during a long flight has transitioned from negligible to statistically inevitable. This threat is not theoretical. It is written in the flight logs and incident reports of aviation history. Perhaps the most famous ghost in the machine incident is the mystery of Qantas Flight 72 in 2008. An Airbus A330 cruising over Western Australia suddenly pitched nose down twice, hurling unbuckled passengers into the ceiling. The investigation found that one of the aircraft's 3 air data inertial reference units had started outputting spikes of garbage data, specifically erroneous angle of attack values. While the exact cause was never definitively physically recovered because particles leave no trace, the failure mode was consistent with a single event upset in the unit's memory. The computer was confused by a bit flip, and the software handling that data did not filter out the physically impossible spike effectively enough. This incident reshaped how manufacturers viewed data validity software logic. Another major event was the Halloween storms of 2003. In late October of that year, the sun unleashed a series of X-class flares and CMEs that battered Earth for days. The operational chaos was significant. The FAA's Wide Area Augmentation System, which improves GPS accuracy for landing, was knocked offline for 30 hours due to ionospheric distortion. Airlines had to reroute flights away from the poles to lower latitudes to avoid radiation and radio blackouts, costing the industry millions in extra fuel and delays. Pilots over the Atlantic reported hearing the sun, described as static and interference on headsets, and HF radios became useless bricks for hours, forcing reliance on tenuous satellite links. More recently, looking at the 2025 context, industry reports highlight a massive precautionary update for thousands of Airbus A320 family aircraft. Investigations into a specific uncommanded flight control event traced the root cause to the elevator aileron computer, or ELAC. It was discovered that intense solar radiation could corrupt specific data registers in the ELAC. The vulnerability wasn't that the chip failed, but that the software running on it didn't perform a redundancy check often enough to catch the bit flip before acting on it. The solution wasn't to replace the hardware, which would take years, but to patch the software to double-check the math. This is a perfect example of software being the shield for hardware vulnerability. So, how do engineers build computers that survive a radioactive war zone? In space exploration like satellites and Mars rovers, engineers use radiation-hardened or rad-hard chips. These are custom-built processors using sapphire substrates instead of silicon to prevent latch-ups, and they deliberately use older, larger transistors because they are harder to flip. They also use shielded packaging with ceramic or heavy metal caps. But there is a problem for aviation. Rad-hard chips are incredibly expensive, sometimes 100 times the cost of consumer chips, and they are incredibly slow, often generations behind current tech. Commercial aviation needs the processing power to run complex fly-by-wire systems and graphical cockpit displays. They cannot run modern software on 1990s-era space chips. Therefore, aviation has moved toward commercial off-the-shelf components to save weight and cost. To compensate, they are adopting new materials like wide bandgap semiconductors. Gallium nitride and silicon carbide are the future of avionics power electronics. Unlike silicon, gallium nitride has very strong chemical bonds. It requires much higher energy to displace an atom in its lattice. Interestingly, these transistors are naturally radiation transparent. They do not accumulate charge in the same way silicon does, making them nearly immune to total ionizing dose effects and far more resistant to single event effects. One might ask, why not just line the avionics bay with lead? The answer is weight. In aviation, every kilogram burns fuel. But there is another reason. High-energy cosmic rays hitting a lead shield can actually make things worse. When a fast proton hits a heavy lead nucleus, it shatters it, creating a shower of secondary particles like neutrons and pions that spray into the electronics like shotgun pellets. Sometimes, less shielding is safer. If the hardware is vulnerable, the software must be invincible. This is where the true ingenuity of modern avionics lies. If a bit flip is inevitable, the software must be designed to treat it not as a catastrophe, but as a routine annoyance to be swatted away. The gold standard of avionics safety is triple modular redundancy, or TMR. The concept is simple. Instead of one computer flying the plane, you have three. Computer A, B, and C all calculate the elevator position. If computer A says move up 5 degrees, computer B says move up 5 degrees, but computer C, having been hit by a solar particle, says move down 10 degrees, the voting logic intervenes. It sees that A and B agree, while C is the outlier. It ignores C, executes the command from A and B, and resets computer C to fix its memory. To prevent a generic software bug from crashing all three, they often use dissimilarity, running different software builds, or using different processors so they do not all have the same physical weaknesses. For smaller components where you cannot fit 3 computers, Engineers use lockstep dual cores. This involves two processor cores on the same chip running the exact same code, line by line, synchronized to the same clock cycle. At every single operation, a comparator circuit checks if the output of Core 1 matches Core 2. If a solar particle flips a bit in Core 1, the outputs will mismatch instantly. The system detects the fault within microseconds, freezes the output to prevent the bad command from reaching the wings, and triggers a rollback to the last known good state. As AI and machine learning enter the cockpit for autonomous landing or fuel optimization, the math gets complex. TMR is too expensive computationally for massive AI matrices. The solution is algorithm-based fault tolerance. This uses mathematical checksums embedded within matrix operations. When the flight management system multiplies two huge matrices to calculate a route, it also calculates a checksum row. If a bit flip corrupts a number in the matrix, the checksum will not balance at the end. The software knows the answer is wrong without needing to run the whole calculation twice. Another technique is software-implemented fault tolerance, or SWIFT. This involves compiling the software with immune system features. One such feature is control flow assertions. The software knows it must go from step A to step B to step C. If a particle strike makes the processor jump from step A directly to step C, ghost variables inserted into the code will detect that step B was skipped and trigger a reset. There is also heartbeat monitoring, where a separate, tiny hardened circuit watches the main software. The main software must send a pulse signal every 10 milliseconds. If the software gets stuck in a loop or crashes due to radiation, the pulse stops and the monitor reboots the system. Additionally, every stick of RAM in an avionics box uses error-correcting code, or ECC, memory. Using Hamming codes, the memory stores extra parity bits for every 64 bits of data. If one bit flips, the math of the parity bits reveals exactly which one it was. The memory controller flips it back to the correct value instantly, often without the main CPU even knowing it happened. This is known as transparent scrubbing. Aviation is built on standards, and regulators have moved from awareness to mandate regarding the solar threat. The primary international standard is IEC 62396, titled Process Management for Avionics, Atmospheric Radiation Effects. It forces manufacturers to calculate the failures in time rate due to neutrons for every component. It mandates that if a critical system has a predicted upset rate higher than 1 in a billion flight hours, it must have architectural mitigation like TMR. There are also standards like DO-254 for hardware, ensuring chips are tested against radiation models, and DO-178C for software. Recent supplements to DO-178C require the software to handle abnormal inputs robustness. A bit flip is essentially the ultimate abnormal input, and software must be proven to recover from these hardware-software interface faults. Hardware and software can only do so much. Sometimes, the only winning move is not to be there. Airlines now have space weather desks alongside their terrestrial weather teams. They rely on data from the NOAA Space Weather Prediction Center, which issues alerts for geomagnetic, radiation, and radio blackout scales. They also use the DSCOVR satellite. Parked 1 million miles from Earth at Lagrange Point 1, this satellite acts as a tsunami buoy, detecting the solar wind speed and magnetic field 15 to 60 minutes before it hits Earth, giving airlines just enough time to ground a flight or change a route. New platforms like FlashWeather AI and Tomorrow.io are integrating space weather into flight planning. If a severe geomagnetic storm is predicted, the software automatically calculates a non-polar route, perhaps flying over the Pacific instead of the Arctic. It balances the extra fuel cost against the risk of radio loss and radiation exposure. Dispatchers will also cap flight altitudes during solar events, as flying lower drastically reduces the neutron flux. The human element remains critical. When the HF radio goes dead over the North Pole, pilots have protocols. Most modern polar jets have iridium satellite phones as a fallback, though massive solar storms can sometimes jam these too. Pilots may resort to blind broadcasting, transmitting position reports on designated frequencies hoping nearby aircraft hear them. In severe cases, captains make the call to turn around or divert, though better protocols today often allow them to continue if GPS accuracy remains within limits. We are currently entering the peak of solar cycle 25, predicted to be one of the most active in recent history. The stakes are getting higher. The rise of urban air mobility, such as flying taxis and autonomous cargo drones, presents a new challenge. These vehicles will not have a pilot to reset a computer. Their software must be fail-operational, meaning it can suffer a radiation hit and keep flying without a millisecond of interruption. This will drive the adoption of advanced AI-based fault tolerance and dissimilar redundancy. The future also involves active sensing. Instead of relying on models, new chip-scale radiation sensors will be embedded directly into avionics suites. The plane will feel the radiation spike in real time and automatically request a lower altitude from ATC, just like it avoids turbulence today. But the ultimate threat remains a Carrington event. In 1859, a solar superstorm set telegraph wires on fire. If such an event happened today, it would likely overwhelm even TMR systems. Aviation aims to ensure that even in this doomsday scenario, the basic analog backup or the most hardened digital core remains alive enough to allow pilots to land the plane visually. The battle between solar storms and software is a testament to human ingenuity. We have taken the chaos of a star, random, violent, radioactive explosions, and tamed it with the logic of mathematics and redundancy. Every time you fly, you are being protected by a silent shield. It is built of gallium nitride atoms, error-correcting memory algorithms, and triple-voted decision logic. The sun will always be throwing punches at our technology. But as long as the software engineers keep writing code that expects the unexpected, the planes will keep flying, safe above the clouds, indifferent to the storm raging in the void above. This is the new era of aviation, where meteorology meets astrophysics, and where software is the only thing standing between a bit flip and a bad day. Thank you for listening to G Fun Facts Online.